Hello student, welcome back to electrochemistry class. We would like to focus on electrochemical series and its fundamental applications. Before reaching to this topic, we just want to refresh the electrochemistry and its concept by using the Nernst equations. Right? So today's our lecture is focused on electrochemistry and by using the Nernst equation, what are the fundamentals ideas that would be necessary to understand the cell potential in electrochemistry, so that can be easily understood by the graphical representation of the Nernst equation, right? So as in the previous lecture, what I have studied is the Nernst equation, right? So this equation is a fundamental equation, so that gives the relationship between cell potential, right, at a temperature T, and this is standard cell potential, which is a fixed at 298 Kelvin and 1 molar electrolyte solution and 1 atm pressure, right? So R is the gas constant, T is the temperature, or N is the number of electron transferred in a electrochemical reaction. F is the Faraday constant, right? And the term, that is natural logarithm ln Zn2 plus and Cu2 plus. So this is the Nernst equation for zinc copper galvanic cell, which has been explained in the previous lecture nicely, right? So what you observe here, E cell, E naught cell minus RT upon NF ln Zn2 plus Cu2 plus, right? So this can be understood by graphical representation, right? So suppose this can be expressed in such a way that y is equal to minus mx plus c, right? So here minus m is slope, right? And this is the equation for linear line. So this can be treated as linear equation. So suppose we just draw x-axis and y-axis, right? So RT upon NF, that is minus RT upon NF. So here we can this value will be m, right? And ln Z plus 2 and Cu2 plus, so this will be ln Zn 2 plus and copper 2 plus, right? So the ratio of these two ions in a natural logarithm form, and E cell will be the y-axis. So this is the E cell, right? Now this C is the intercept, which is equivalent to this. So this is C. Because here minus sign is fixed in this equation, so this means the linear line does not go from the origin point. This is origin point, right? So in the positive direction. So rather the value of y-axis will decrease linearly, right? So the value of y will decrease linearly like that. It means E cell decreases with ln Zn2 plus and Cu2 plus, right? So depends on the concentration ratio of this value. So this E cell changes. So here change of cell potential in a electrochemical cell actually depends on the natural logarithm of this ratio, right? So here the lowest ratio, here the value is increasing towards x-axis in the forward direction. So at 0 point it is maximum, right? And this value, so this value is called E0 cell, right? Which is a standard cell potential at standard state. Okay, so this is intercept on y-axis, and now this E cell value is maximum at 0 point, right? So once this is the value increases, then E cell decreases, right? Ultimately it is decreases to this. It means higher the value of ln Zn2 plus Cu2 plus, the lower will be cell potential, right? So this equation clearly signifies that the overall, the value of this decides whether cell potential will be high or low, right? So the graphical representation of this Nernst equation look like that. So electrochemical cell potential linearly decreases with respect to ln Zn2 plus and copper 2 plus. Clear? Now E cell, as you know in the previous lecture, E cell equal to E naught cell minus RT upon NF and ln K, right? So where K is the equilibrium constant, right? So in the previous lecture you have seen that delta Z naught plus RT ln Q, right? So Q is the reaction quotient. So Q can be transformed in equilibrium constant once the redox reactions or cell reactions reaches to a equilibrium state. Okay, it means the cell potential tending towards 0 once Q is replaced by equilibrium constant, that is K. So what happens here? E cell, E naught cell minus RT upon NF ln K. At equilibrium, E cell equals to 0, right? So here we put the value 0 and we will separate these values. So we will get E naught cell, that is RT upon NF ln K. So again this look like a straight line, y is equal to mx, right? Where m is the slope and r is the gas constant. If T is the fixed, which is a 298 Kelvin, n is the number of electron, so that is a fixed quantity. F is Faraday constant, which has a 96,500 Coulomb per mole. That is a overall, these four parameters are constant, right? So it can be treated as slope m, and the variation parameter is ln K, right? So what graphical representation can be extrapolated here. Suppose this is a x-axis and this is your y-axis, right? So on the y-axis is standard cell potential E naught cell, right? And on the x-axis the variation parameter is ln K. So this is your ln K, right? And this is your E naught cell. Since it is a equivalent to a straight line, y is equal to mx, right? So the linear line will be increases from origin point. So this is your origin point. Okay, so if x is 0, then y is 0, right? If x is 1, then y is accordingly changes. So this value, if the value of ln K increases, then it look like that. What does it mean? If the value of ln K increases in the x direction, or in the positive x direction, the standard E cell also increases, right? So from origin point it is increasing. So it means the cell reactions are thermodynamically favorable. Because the equilibrium constant is very, very high. So higher the value of equilibrium constant, so it justified the thermodynamic reactions in the forward directions, and there is a chances of the formation of the products. So the higher the value of L and K, the higher will be standard cell potential. So this is the linear increase and relation between the standard E cell and L and K, and this is actually graphical representation of E cell versus Ln concentration of that is Zn2 plus and copper 2 plus ratio, right? So these are the two graphical presentation, so that can insight to understand the electrochemistry involved in the Nernst equation, right? So further this equation can be transformed like that. So that is Ln K, and here Nf going in this cross multiplication. So Nf E naught cell, that will be RT, right? So this all these are constant Nf upon RT, and finally E naught cell is actually standard cell potential. So here just we transform this equation. K is equal to exponential Nf upon RT and E cell. So this is exponential equation, right? Here variation parameters are on the y-axis. This is the equilibrium constant. K is the equilibrium constant, and Nf upon RT. So that is you can consider it as slope, and variation parameter is E is standard cell potential. So here you just want to draw the graph for this particular equation. So this is actually y-axis, and this is on x-axis, right? So on y-axis the value will be K, right? So this is your equilibrium constant, and on the x-axis it will be E naught cell, right? So what happens here? The value of K, equilibrium constant, increases exponentially, right? So larger the value of standard cell potential, higher will be equilibrium constant. So this is the exponential representation of Nernst equation, and equilibrium constant exponentially increases once the value of standard cell potential increases in the positive direction of x-axis, right? So this is the actually graphical representation that deals and gives us idea about the understanding of variation of cell potential with respect to various parameters, right? So that parameters must be understood so that the concept would be clear for the electrochemical analysis or electrochemical studies, right? So this is the actually ideas so that have been refreshed to you. So because without Nernst equation, electrochemistry is insignificant. So we have to understand the idea and scientific terms and graphical variations in the cell potential, so that we can apply in the various sector by using the electrochemistry and electrochemical ideas. So now coming across to the main point, so that is electrochemical series and its fundamental applications, right? So what is electrochemical series? The electrochemical series is a set of elements So that has been arranged in a increasing order of standard reduction potential, right? So that series is called electrochemical series. It means uh, this electrochemical series means there is a series from top to bottom, right? So there is maybe metal, non-metal, or acidic half cell reactions or basic half cells reactions. So depending on the standard reduction potential, so they are arranged from top to bottom, right? So they are called electrochemical series, right? So electrochemical series here starts like that. Lithium, so this is element may be either metal, non-metal, or acidic half cell reactions or basic half cells reactions, right? So here some elements, metal, non-metals, and uh, corresponding standard reduction potential have been shown to understand the chemistry of electrochemical series, right? So lithium, potassium, calcium, sodium, magnesium, aluminium, manganese, zinc, chromium, iron, cadmium, nickel, tin, and hydrogen, right? So this is hydrogen. Above the hydrogen, so they are all metals, right? And below the hydrogen, copper, iodine, silver, mercury, bromine, chlorine, gold, and fluorine. So in this chlorine, between chlorine and fluorine, there is also bromine and iodine, you can simply say. So between chlorine and fluorine, there will be bromine and iodine also. So this is a actually brief series. So all the things can't be shown here because of the limitation of these blackboards. So we just try to give a overview about this series, right? So what happens here? All these like lithium, potassium, calcium, sodium, magnesium, they are alkali and alkaline earth metals, right? So here the second column is electrode reactions, right? So electrode reactions means redox reactions, half cells, that is reduction reactions, right? So this is reduction reactions. Suppose all elements they show their reduction, and reduction look like that. So here first we have given lithium plus one electron that receives and then converted back to lithium solid, right? So here lithium shows reduction, so it has standard reduction potential, and standard reduction potential or standard electrode potential is minus 3.05 volt, right? So it has maximum negative, or you can say the minimum potential, or you can simply say the lowest electrode potential for the reduction reaction is minus 3.05 volt, right? But once you move from top to bottom across this series, then what happens? Now, from lithium, then potassium, then calcium. So this negative value actually decreases, and ultimately it reaches towards 0.00 volt. So the lowest negative value, so the lowest negative potential, it is ultimately increases, it means it reaches towards 0.0 voltage, right? So what happens here? So this is your hydrogen. It means if there is a possibility of reduction reaction of hydrogen, so what happens here? 2H plus, right, that receives 2 electron, it is getting back to hydrogen gas. So the resultant standard reduction potential will be 0.00 volt, right? So hydrogen is the only element that show zero potential, right? So either it is oxidized or either it is reduced. So it should be mentioned here. Now above this hydrogen, some metals like aluminum, manganese, zinc, chromium, iron, cadmium, right? So they are moderately metal, and below this hydrogen, some uh, metals like copper, silver, mercury, and platinum also. So platinum also, so they are placed below the hydrogens, right? So what these series indicate that the elements which are above the hydrogens, they have negative standard reduction potential, right? So it means all these elements, they show reduction reactions and have negative standard reduction potential, and the reduction reaction look like that. Mn plus, M is any element, it can take an electron and it is converted back to this metal or non-metal, whatever you select from top of the hydrogens, right? So depending on the number of electrons, so the value of standard reduction potential is fixed. Either 1 electron, 2 electron, 3 electron, doesn't matter. So the characteristic to the metal or non-metals, since above the hydrogens they are all metals, so here M is the metal actually. So standard reduction potential will be actually negative quantity for these metals. So and ultimately it reaches towards zero because this is the hydrogen, right? And below the hydrogen, so these are the elements which are supposed to be present. So for the copper, it has actually E 0.34 volt, right? For the copper, standard reduction potential is positive, right? And ultimately it reaches towards maximum value for the fluorine, right? So fluorine shows a reduction reaction like that. So this is F2 that receives 2 electron, getting back to 2 fluoride minus, that is fluoride anion. So this is the reduction reactions having a standard reduction potential that is very high positive value, that is 2.87 volt, right? Here lithium that show highest negative potential, that is minus 3.05 volt, right? While the fluorine, that is F2, show a highest positive standard reduction potential, right? So what does it mean? So all the metals or non-metals which are present below the hydrogens, they show positive standard reduction potential, right? So E0 read, all are positive, right? And above the hydrogen, so hydrogen is the barrier point, right? So above the hydrogen, all these elements, they show standard reduction potential, it means E0 reduction in a negative quantity, right? So the negative quantity and the positive quantity, so it means the standard reduction potential ranges from minus to 0 to positive value. So this will be the, actually this is 0 and this value will be negative, right? So this value will be positive. So it means standard reduction potential may be negative value, or maybe 0 value, or maybe positive value, right? So this should be clear. Otherwise, if you want to ask any questions at any stage, I will give you more deeper insight regarding that. Okay, so this is electrochemical series, and this electrochemical series are actually based on the reduction reactions at standard state, right? Standard state means temperature 298 Kelvin, pressure 1 atm, and electrolyte solution that will be 1.010 molar, right? So this is the condition of actually standard state. So these are the actually elements which gives us idea about the standard reduction potential. So what happens from minimum value to higher value? A electrochemical series is a series so that have minimum potential to maximum potential. It means the highest negative potential to highest positive potential, including zero potential, right? So what does it mean? So that can be understood very beautifully through the knowledge of the electrochemistry. Okay, so now in the next page, that is applications. So applications, first applications of the electrochemical series is reactivity of metals. So by the knowledge of standard reduction potential, we can predict the reactivity of the metals or non-metals. Okay, so here the all the standard reduction potential above this hydrogen, they are all negative, right? So all negative means all these metals are highly reactive, right? So the highly reactive means lithium has maximum negative point, that is minus 3.05, right? So it is highly reactive, right? And reactivity decreases up to hydrogens. So the most reactive one is the lithium, and least reactive one just above, that is tin, right? So the reactivity can be explained on the basis of variation of this negative standard reduction potential. Now because of the as you know that because of the negative standard reduction potential, so iron actually they are highly reactive, so they react with oxygen in the presence of air or moisture, so they converted back to hematite, that is Fe2O3 or Fe3O4, right? So and after absorption of water from the moisture, they are getting the formation of the rust. So it's so reactivity of the metal, and iron is highly reactive because they react with oxygen to form rust. So all the metals which are present above these hydrogens, they are highly reactive, right? So they are highly reactive. They are highly reactive, right? And larger the value of negative standard reduction potential, higher will be reactivity. Suppose we have magnesium, and we have iron, right? So the highly reactive metal will be magnesium, and lowest reactive metal will be iron, because it has greater negative standard reduction potential compared to this iron, right? And hydrogen has zero standard reduction potential. It means it can either go oxidation or reduction, doesn't matter, right? But rest of the elements that are actually metal or non-metals, so they are actually below to the hydrogens. They all these metal are non-metals, so positive standard reduction potential, right? So positive standard reduction potential means these elements are not too much reactive, right? So, and reactive means all these elements does not undergo oxidation, so they are not easily oxidized, right? So larger the positive standard reduction potential, so greater is the actually capacity to be reduced rather than oxidation. So this is the fluorine, right? So fluorine has highest positive standard reduction potential. It means, so this fluorine is very least reactive, or it can't be oxidized easily, rather it is strongly reduced, right? So this fluorine receives 2 electron and it is getting back to 2 fluoride minus, and which have a standard reduction potential 2.87. So the most reactive metals, they are kept in the above to the hydrogens, and least reactive metals, they are kept below to the hydrogen metals, right? So the least reactive non-metals is fluorine, and the copper is the weakly reactive metals, right? Because of the positive standard reduction potential, and positive standard reduction potential increases from this copper to this fluorine, right? It means the standard reduction potential from top to bottom increases. Clear? Lithium is the most standard, or simply you can say this lithium possesses highest negative standard reduction potential, and this fluorine possesses highest positive standard reduction potential. So all these metals are highly reactive, and all these elements, they are less reactive. So reactivity decreases across the electrochemical series, right? So reactivity decreases. Reactivity decreases, right? So reactivity means loss of electrons from the elements. It means oxidation. So now, so this is the reactivity of metals. So next point is the electropositive character of metal. Electropositive character of metal. So in the electrochemical series, there are 3 types: strongly electropositive. So they are all lithium, potassium, calcium, sodium, magnesium, all alkali and alkaline earth metals. They are strong electropositive metals, right? So they have negative standard reduction potential, and like aluminium, manganese, zinc, chromium, iron, cadmium, nickel, etc. So they are moderately electropositive metals, and below the hydrogen, all non-metal and metals like mercury, silver, mercury, and gold, platinum. So they are weakly electropositive metals, right? So this is the actually application to understand the electropositive characters. Electropositive characters means the metals which have high tendency to lose its valence electron, right? It means they have high tendency to oxidize by releasing their valence electrons. So oxidation capacity of strongly electropositive metals is very high, right? So they have tendency to lose their valence electron, getting back to oxidized form. Okay. Now, so this is the range greater than -2 volt, right? Like lithium -3.0. So this is your strongly electropositive metals, and from 0 to -2 volt, approx 0 to -2 volt, just above the hydrogen. So all these metals like aluminum, zinc, iron, they are moderately electropositives, and copper, mercury, silver, they are weakly electropositive metals. So electropositive character of the metals can be explained by the knowledge of standard reduction potential in a electrochemical series. Nice. Now third application of this electrochemical series is to predict whether a given metal will displace another from its salt solution or not. So that can be understood through the knowledge of standard cell potential. As you know that when a electrochemical cell is formed, like galvanic cell, suppose we have zinc copper galvanic cell, right? Galvanic cell. So what you have observed, when zinc rod is dipped in copper sulfate solution, now what happens? This displaces the copper, that is zinc SO4 plus copper is precipitated as copper solid. So this is the overall cell reactions in a zinc copper galvanic cell, and the overall cell potential E0 cell, as you have earlier studies, it is 1.10 volt, right? So because of the positive standard cell potential, this reaction thermodynamically favorable, right? So it means the formation of products is actually thermodynamically favorable. It means, what is this third point? To predict whether a given metal, so suppose here this is a zinc rod, so zinc metal, so that is dipped into the copper sulfate solution, right? So once the zinc rod is inserted in copper sulfate solutions, now, so what happens? Then because of the standard reduction potential, which are negative to that of the copper, so they are highly reactive. So zinc is highly reactive compared to copper. So this zinc easily displaces, right? So this copper from the solution and itself attached with this sulfate anion to form zinc sulfate, right? So this is zinc sulfate and copper is precipitated out, that is copper solid. So because it is oxidized easily, it means, so they are highly reactive. So the zinc is more reactive compared to copper, right? So it is easily oxidized into Zn2 plus. So that is why this zinc is susceptible to displace this copper from the copper sulfate solution as a copper solid. So this type of prediction can be explained in a variety of cell potentials, variety of cell reactions in an electrochemical cell. Suppose in place of zinc, if you want to add a silver wire, right? So then the predict the possibility of the reactions. So this silver is below than the copper in the electrochemical series, right? So this silver is less reactive compared to copper, right? So this silver can't displace copper from the copper sulfate solution to form silver sulfate and copper solid. So because of that is silver Ag is less reactive compared to copper, right? So silver can't displace this copper from the solutions, and this reaction is thermodynamically non-favorable. It means reaction does not happen, and this is the actually applications that is arising from the electrochemical series. So there are variety of cell reactions that can be actually explained on the basis of the standard reduction potential and their reactivity in this series, right? Now the fourth point is the most important, right? So that is reducing and oxidizing power of elements in electrochemical series. Now question is what is reducing agent or what is oxidizing agent? The reducing element is element having tendency to lose its valence electron, means it is getting back to oxidized, right? So they are called reducing agent. It means once this metal undergo Mn plus n electron, right? So this uh, Hoff reactions or this reaction tells us that the metal is going to be oxidized to form Mn plus, right? So it means this metal is reducing. So in the electrochemical series, uh, which elements are highly reducing and which elements are weakly reducing? So that can be understood through the knowledge of standard reduction potential. Now, what is the oxidizing power? What is the oxidizing power? Oxidizing power is defined as metal having susceptibility to gain electrons, right? So then it is reduced like m n plus n electron, it is getting back to m. So here oxidation number decreases. It means there is a reduction reaction. In the determination of oxidizing power, we just explain the reduction reactions, and in the reducing power, we just explain the oxidation reactions. They are complementary to each other, they are reverse to each other. So in the electrochemical series, you have seen that the most negative standard reaction potential actually exists as minus 3.05 volt for lithium. What does it mean? Lithium has a strong tendency to lose its valence electron, right? So it has a strong tendency to Li, it is getting back Li plus electron, right? So it is oxidized. It means they are highly reactive, so they are highly easily oxidized. So by releasing the valence electron, right? So this is the most and strong reducing agent, right? So strong reducing agent in overall electrochemical series, the strong reducing agent is lithium, right? So lithium onwards reducing character decreases. It means, so this is the most and strong reducing agent, and accordingly negative potential changes, right, and approaches towards zero. So the this is the actually tin. So you have just hydrogens. So they are reducing, but they are less reducing compared to this lithium. But after this hydrogen, what happens? They have all standard reduction potential positive, right? So because of positive standard reduction potential, so they have poor tendency to uh, lose its valence electron, right? So they are weak reducing agent, and that is weakest reducing agent, that is weakest reducing agent. Fluorine is the weakest reducing agent, and strong reducing agent, that is lithium, because of highest negative standard reduction potential, and it has highest positive standard reduction potential. So that is why they are weakest reducing agent. Clear? So reducing power decreases from lithium to fluorine. Clear? So this is the electrochemical series where reducing power decreases. Lithium is the most reducing metal, and fluorine is the weakest or least reducing non-metal, right? So this is the actually electrochemistry behind the idea of reducing powers. So reducing capacity decreases, reducing power decreases from top to bottom. Okay. Now oxidizing power, it means oxidizing power means it has tendency to gain electron to convert it back into the neutral metal, right? So the standard reduction potential, right? Standard reduction potential, if it has very high positive potential, then the elements show greater tendency to be reduced. So in the electrochemical series, what you have observed, so that can be easily seen from the series. Now here you can see, so this is copper, and the standard reduction potential, it is plus 0.34 volt, right? Now this fluorine has 2.87 volt, right? So because of positive standard reduction potential, so they have a tendency to attract, or gaining capacity of the external electron is very high for the fluorine. So fluorine is the most and strong oxidizing element. So this is a strong oxidizing element, right? So it can easily accept two electrons converted back to this fluoride anion, right? But once you move from bottom to top, then oxidizing power decreases. So least oxidizing element is lithium, right? So this is least oxidizing element. So lithium is the least oxidizing element or weakest oxidizing element, while fluorine is the strong or highest oxidizing agent. And all the atoms in between these two, they changes accordingly. So in case of halogen family, now that is F2, Cl2, Br2 and I2, right? So this fluorine is the most and strong oxidizing element compared to this iodine. So iodine is the weakest oxidizing agent in this halogen family, right? While fluorine is has highest oxidizing power, right? Clear? So it can be understood through the knowledge of standard electrode potential. So all these non-metals have positive standard potential, but standard potential decreases, right, from plus 2.87, so it is decreased, but in a positive quantity. Clear? Now fourth point is clear. Now fifth point, E cell calculation, right? So suppose we have any electrochemical cell, either galvanic cell or electrolytic cell, so we can calculate easily through the half cell reactions of a complete cell potential. So standard cell potential, that will be standard reduction potential and plus standard oxidation potential. So these two value is added to get the standard cell potential. Clear? Or simply you can say this E0 cell will be E0 cathode minus E0 anode. So both these values is standard reduction potential, right? So for the reduction reaction, it is standard reduction potential. For the oxidation reaction, it is also standard reduction potential. Clear? So if we have a two standard reduction potential, then we can easily subtract from cathode minus anode, then we will get resultant standard electrode potential or cell potential, right? So there are various combinations of metals to get the electrochemical cell, and we can get the resultant standard cell potential, right? Like galvanic cell, that is zinc copper cell, where we have calculated E cell, that is 1.10 volt. Feasibility of redox reactions. The seventh point is the feasibility of redox reactions. Means complete overall cell reactions, whether it will go or proceed in the forward direction or in the reverse directions, that can be understood through the correlation of standard reduction potential, right? So if, since all of you know that any electrochemical cell is composed with two different metals like anode and cathode, clear, and they have different standard reduction potential, right? And after the combination or coupling of these two elements to form a electrochemical cell, we can get a resultant cell potential at standard state. So if we have E naught cell, right, through a particular combination of anode and cathode, the value of E cell must be positive, right? So it means the cell reactions are thermodynamically favorable. So there may be chances of formation of the products in the forward direction. Clear? In fact, you know that delta G equal to minus NF E naught cell. So this equation clearly demonstrating that E naught cell should be positive, right? Then only we can get delta G negative. And delta G negative indicates the cell reaction is thermodynamically favorable. Means there is a probability that the reaction will proceed in the forward direction. So there may be formation of the product that favors the formation of product. Okay. Suppose we have a cell reactions like that. Here nickel is the element, so that is inserted in the copper sulfate solution, right? So it gives nickel sulfate plus copper as precipitated as solid. So this is the electrochemical cell, that is galvanic cell, a type of galvanic cell, and the cell potential at standard state, that is E naught cell, is equal to E naught C minus E naught A, right? So both are the standard reduction potential. So in case of, in the electrochemical series, right? So the copper is just actually below compared to nickel, right? So nickel is just above the hydrogens, right? But this copper is below the hydrogens. So the reactive metal is nickel. So nickel is highly reactive compared to copper. So they can react this solution and easily displace this copper. So this is converted back to nickel sulfate, right? So here nickel is oxidized nickel sulfate and copper sulfate is getting reduced. So copper. So the resultant standard cell potential, that is 0.59 volt. So it is a positive quantity. So ultimately, if you put this value here for inert cell, then you will get delta G is negative quantity, right? So this confirms that this cell reaction is thermodynamically favorable and it is feasible, and there may be chances of formation of the product like nickel sulfate and copper. So such type of cell reactions actually can be uh, constructed to get the negative Gibbs free energy change, and the negative value of Gibbs free energy change indicates the reactions are thermodynamically favorable and it can proceed in the forward directions, and there may be chances of the high chances of the formation of the products. Okay, now prediction of the electrolysis or electroplating. So we have suppose we have water. Water may contain Na, Cl minus, H plus, I minus, right? So these are the sodium chloride ion, hydrogen ion, and iodide ion. Suppose any water, if you have a water, and we want to set up a electrolytic cell for the electrolysis of water. So in the previous lectures, we have constructed electrolytic cell, and we have given an insight on the anodic and cathodic reactions in a electrolytic cells. So anode is actually act as a platform for the oxidation, and cathode is a platform for the reduction. So as you know that the standard reduction potential, so it has most negative quantity, right? So this has 0 volt, right? So these chloride ion and iodide ion, they are both below to the hydrogens, so they have positive standard reduction potential. Cl minus and I minus both have positive standard reduction potential, right? So the reduction of the hydrogen ion, right? So actually H plus electron, it is actually converted back to H. This is 2H, 2 electron, and H2. So there may be chances of formation of hydrogens, right? So if we have a mixture of ions in a solutions like that, so we can predict the electrocatalysis of the elements depending on the standard reduction potentials. So in Na and Cl, Na plus and Cl minus, right? So Na plus, it is actually reduced by receiving this electron to Na solid, right? And Cl minus is oxidized at the anode. So because of standard reduction potentials, So it has high positive and it has negative standard reduction potentials. So this Na plus is easily reduced. Okay. So the knowledge of the standard reduction potential, electrocatalysis can be predicted. Now corrosion of the metals, right? So the most reactive metals in the electrochemical series, they undergo corrosions. So because of the its reactivity, right? So higher the reactivity, higher will be capacity to be corroded. So corrosion means we have shown the Hopf cell reactions that are taking place in the formation of the corrosion. So that is iron solid. It is oxidized Fe2 plus in the moisture or aqueous system by releasing 2 electrons. And this is oxidation reactions, right? So this oxidation reactions is actually Hopf cell reactions, so which have a standard reduction potential for the oxidation reaction is minus 0.044 volt. Clear? But this oxygen from the environment and that is hydrogen ion from the moisture will receive 4 electron, that is converted back to 2H2O, that is liquid water. And this is reduction reactions which have positive 1.23 volt, right? So in the corrosions, so once the corrosion takes place, so they set up a electrochemical cell, that is galvanic cell, and actually cathodic and anodic reaction takes place, and overall just adding these two Hopf cell reactions, we will get the final cell reactions like that. So this 2 mole iron solid, so once react with 1 mole of oxygen in the presence of hydrogen ion, so it is getting oxidized as a Fe2 plus. So here Fe is in 0 oxidation state, here it is plus 2 oxidation state. So this iron is oxidized in Fe2 plus by formation of the water, and overall this electrochemical galvanic cell standard cell potential, that is E naught cell, is equal to 1.67 volt. So for the combined effect of these two Hopf cell reactions, what we get here, E naught cell is equal to 1.67 volt, that is a positive quantity. It means delta G is negative, right? So thermodynamically, these reactions are possible and feasible. So that is why iron metal undergo corrosion and to form the rust. So this is thermodynamic feasibility of the iron, and we can protect the corrosions. Suppose we have iron, right? So it is Fe2O3 into X2O. So this is actually rust, which is called corroded iron, right? So once this iron comes into the contact of O2, air, moisture, so this form composition Fe2O3 into X2O or Fe3O4 into X2O, right? So this is rust. So if you want to prevent the formation of rust on the surface of iron, then what process or techniques can be adopted to prevent this corrosion? So in the electrochemical series, what you have seen, where is the position of this iron? So this is iron. Above all the elements, they are highly reactive, so they can easily react with oxygen. So they cannot prevent the corrosion that occurs on the surface of iron. So what we have to uh, adopt here, the below this iron, any of the metal like cadmium, nickel, tin, right? So any metal can be taken to construct a galvanic cell, right? Suppose we just take nickel. So what happens? Nickel is below to the iron. So iron and nickel, suppose. So this is highly reactive, and because of the reactivity, it forms rust and it is corroded. But nickel is less reactive, so it is not easily oxidized, right? So it can be electroplated on the surface of iron. So this is your iron, right? And on the surface, we can electroplate by nickel. Because of the poor reactivity of the nickel, and the poor reactivity comes from the standard reduction potential. So it has lower negative compared to this iron. So iron is highly reactive, so it is getting corroded, and once the electroplating is performed through the nickel, then it is prevented. So iron can be electroplated through nickel to prevent the corrosion. So any of the metals that are highly susceptible to be corroded, so that can be prevented through the electroplating or by covering a thin film on its surface, so that the reactivity is lowered down on the topmost elements, and the desired metal may remain safe and sustainable. So this is what is the actually electrochemistry and its application, and that is basically through the knowledge of the standard reduction potential. So the most important parameters, that is standard reduction potentials. So if you have a electrochemical series, and if you want to apply the electrochemical series, then we must know the characteristics standard reduction potential, and which one undergo easily oxidation, which one easily undergo reductions, and depending on the oxidation reduction characteristics of the elements, we can combine, we can couple to each other to form a variety of electrochemical cell or galvanic cell, and electroplating, sometimes electrowinnings and electro-refining process that can be applied at a industry levels to protect the corrosions or from any other undesired electrochemical reactions. So these are the beautiful concept and ideas. I think that much is sufficient, and it will give you more insight to understand the electrochemistry of the electrochemical series and its significant applications in the various sectors. So if you have any confusions, you can arise questions and ask with full discipline, and I will try to give you more positive response in these regards. So thank you, students, and I hope this video lecture would be more beneficial and for your understanding, and it will activate your brain power, right? So please don't forget to like, share and comment on this particular video. So thank you, students. I will meet you again by another video, right?